Hello everyone, I am Himanshu Mishra. So until now we have discussed question from the kinematics where we have discussed the kinematics problem in the Cartesian and in the curvilinear problem. We also solved few problems from the polar coordinates and we are still left with few problems. So in this tutorial we will be solving few problems from the polar coordinate, and then I will move to the absolute motions or the few more problems from the absolute motion and the relative velocity concept. So let's start with some of the polar coordinate problems. So we already have solved few problems in the polar coordinate and in the curvilinear coordinate, and we know how to calculate the velocity and acceleration and their components, and then how to calculate the overall magnitude of velocity and acceleration. So in the remaining few problems from the polar coordinate, we will be following the similar concepts. There is nothing new here. So in this question, we have a radar gun at O rotates with the angular velocity of theta dot 0.1 radian per second and angular acceleration of theta double dot at 0.025 radian per second square at an instant of theta equals 45. As it follows the motion of the car traveling along the circular road having a radius of r 200 meter, determine the magnitude of velocity and acceleration. So this is kind of a similar question that we have solved in the last week. So here also we need to determine the magnitude of acceleration and velocity. So we will follow the previous concept that first we need to find the component of velocity and acceleration, and then once we found out the component, then it is very easy to calculate the magnitude of both. So let me write down the quantities which are given here. So we have given the theta dot, which is 0.025 radian per second square, and this is theta double dot, and theta dot is 0.1 radian per second. So we have given r, which is 200 meter, and we can see it's a constant, which means that r dot and r double dot will be 0, right? So the radial component of velocity will be r dot, which is 0, and then the theta component will be r theta dot, which will be, so r is 200 meter and theta dot is 0.1, so v theta will be 20 meter per second, right? Similarly, so here we already got two components, vr and v theta. So my magnitude of velocity will be vr square plus v theta square. So vr is 0, which means my velocity will be, magnitude of velocity will be 20 meters per second. Similarly, we can write down the expression for component of acceleration in the polar coordinate that we have looked in the previous class, and which is, so here the radial component of acceleration will be r dot minus r theta dot square. So it should be r double dot, and so r double dot is 0, which means, and r is 200 and theta dot is 0.1, so it is 0.1 square, so it is 200 multiplied by 0.01, so r is minus 2, right, meter per second square. And in the same way we have r a theta, which is r theta double dot plus 2r dot theta dot. So we know that this term will be 0 because r dot equals to 0. So a theta will be r theta double dot, r is 200 and theta double dot is 0.025 radian per second square. So a theta will be 5 meter per second square. Right, so to find the magnitude we have ar square plus a theta square under root. So it will be 4 plus 25, so a will be root 29, which will give acceleration as 5.38 meter per second square. So this is my value of acceleration. So you can see that like the previous problems, we just need to calculate the component of velocity first, and then from this expression we can actually calculate the magnitude of velocity. And we have done the similar thing with the acceleration. So first find the acceleration in the radial direction and then in the theta direction. Once you got that, then you can use this expression to calculate the magnitude of acceleration. So from the last week we are doing similar problems but in a different coordinate system. We have done same thing in the curvilinear coordinate system, where we define the velocity and acceleration component in the normal and tangential direction and in the Cartesian coordinate as well. And here we did in the polar coordinate. So the problems are similar. It just look from the diagram or the question that it might be difficult or it might be a different, but once you identify the parameters like r, theta, r dot, theta dot, r double dot, theta double dot, once you identify these parameters, it is very easy to calculate the component of vr, v theta, velocities, and component of acceleration like ar and a theta, because component of velocity and acceleration are made from these 6 variables. So first identify these 6 variables. Once you identify these 6 variables, it is very easy to calculate these components, and once you find the components, and you can actually easily get the magnitude of velocity and acceleration. So this should be your first objective, to find these 6 variables. So let's solve one more problem here. So here we have given a slotted link is pinned at O, and as a result of the constant angular velocity theta dot equals 3 rad per second, it drives the pack P for a short distance along the spiral guide, which is r equals 0.4 theta, where theta is in radians. Determine the velocity and acceleration of the particle at the instant it leaves the slot in the link when r equals 0.5 meter. So as I said that your first objective should be to determine these 6 variables, because the component of velocity and component of acceleration all are made from this 6 variable, r theta, r dot theta dot, and r double dot theta double dot. Once you figure out these 6 variables, you can easily find the component of velocity and acceleration, and then you can find the magnitude of velocity and acceleration. So first let me write all these 6 variables here. So from the question we have given that the theta dot is constant, right? Theta dot is constant, which is 3 rad per second, which means theta double dot is 0, because rate of change of theta dot is 0, because this theta dot is constant, which will give us this quantity theta double dot is 0. And we have given r, which is 0.5 meter, and we have given the relation of r and theta, r equals 0.4 theta. Right, now when we differentiate this quantity, we twice differentiate this quantity, we will get r double dot equals 0.4 theta double dot, and we know that theta double dot is 0, which means it will give r double dot equals 0 as well. Right, so how many quantities we figure out? We figure out r double dot, theta double dot, we know theta dot, we know r. So still we need r dot and theta, which we can get from here. Theta we will get from here, and r dot we can even get r dot from this equation. So if I differentiate this expression here, I will have r dot equals 0.4 theta dot. So r dot equals 0.4, theta dot is 3, so my r dot will be 1.2 rad per second. So okay, so this also we found. So let me write down first r theta, r dot, theta dot, r dot, double dot, theta double dot. So we found this quantity, we have this quantity, we know this quantities, we know this, and now only theta is left, and theta we will find from this expression, which is r equals r divided by 0.4 equals theta. So my r is 0.5, so theta will be 0.5 divided by 0.4. So it's theta is 5 by 4, right? So theta is also there. So we found these 6 quantities, and we know that my velocity component Vr and V theta and acceleration component Ar and A theta entirely made from these 6 quantities, which we already figured out. So we can easily find the magnitude of velocity and acceleration. So my velocity Vr will be r dot. So Vr r dot, which is equal to, r dot is 1.2 rad per second. So it is 1.2 rad per second. And my V theta equals r theta dot. So my r is 0.5 and my theta dot is 3 rad per second. Sorry, it should not be rad per second. So it will be V theta 1.5 per second. Right? So my magnitude will be Pr square plus V theta square. So it will give me 1.2 square plus 1.5 square. So on calculating, I will get magnitude of velocity 1.92 meter per second. And in a similar manner, we can actually calculate the magnitude of radial acceleration and the angular acceleration, which is the radial acceleration is r double dot minus r theta dot square, and we know that theta double dot and r double dot was 0. So it is reduced to r theta dot square. So my r is 0.5 and theta dot is theta dot is 3, which is come out to be 9. So it is minus 4.5 meter per second square. Similarly, A theta will be r theta double dot plus 2r dot theta dot. So my theta double dot is 0, which will give me 2r dot theta dot. So A theta will be 2. So my r dot is 1.2 and theta dot is 3. Which will give me acceleration 7.2 meter per second square. So now I can calculate the magnitude of acceleration, which is ar square plus a theta square, which will give me 4.5 square. So I am not writing minus sign, because when I square this, it doesn't matter. And 7.2 square So on calculating, I will get magnitude of acceleration as 8.7 meter per second square. So again we have used a similar concept that first we figure out the all 6 variables of r and theta, here, and then since the component of velocity vr and v theta and the component of acceleration ar and a theta made entirely from these 6 variables, I can actually easily find these components and then can easily calculate the magnitude of velocity and the magnitude of acceleration, right? So let's start with this weak problem. So until now we have looked how to calculate the velocity and acceleration in the Cartesian coordinate, in the curvilinear coordinate, where we define the components in the normal and tangential uh, form, and in the polar coordinate where we define the components in the radial and angular direction. And we have last week we have also solved few conceptual problems, that how we are going to distinguish between the displacement, which is a vector quantity, and distance, which is a scalar quantity. So we figure out that we have given a system where a particle is moving in a random direction, how to define the displacement in the vector quantity, since it is a vector, and how to define the distance, and it come out to be a scalar quantity. Then we also solve one problem where we have defined the displacement vector, and then we find out the velocity by taking the time derivative of displacement vector. So we found the velocity vector when we take the time derivative of displacement vector. And we also find problems where we have to define the distance or displacement, components of displacement in the scalar form, such that if we take the time derivative we will get the component of velocity in the Cartesian coordinate in the scalar format. Similar concept we use in the curvilinear and in the polar coordinate as well. So in this week we will try to solve more absolute motion problem. And in this types of question, what happens that there is a connection in the system. For example, here you can see there is a rod AB which is connected to CD, and when any of this part moves, the other members also moves. So it produces, so one part actually produce a motion, absolute motion, which make other part also move, and we need to find the uh, variables like angular velocity, velocity, acceleration on the other part. So this will be, we will be looking in first few problems, and then we will move to the relative velocity problem. That if we have given the velocity at one end of the joint, then how to find the velocity at the other end from the perspective of the previous end of the joint. So we will be solving this question in today's class. So let's start with the first problem. So here we have given the mechanism is used to convert the constant circular motion omega of rod AB into translating motion of rod CD. Determine the velocity and acceleration of CD for any angle theta of AB. Right, so we have given a length AB, and it is moving with some angular velocity omega. It is making an angle theta, and we have a distance x here. And let's say the length of this rod is L. Okay, so we can see that it actually produces a motion in the horizontal direction. It is actually moving a length CD. So this is my CD, and you can see that as this rod AB is actually rotating, it actually producing the horizontal motion CD, right? So here I can write X as L cos theta. Now since X is changing with time because of this angular motion of the rod, I can differentiate this expression in time, and I can write X dot equals minus L sine theta, theta dot. Because this X is changing, because this omega, because this rod AB is rotating, and in the question, given in the question, due to this rotation, there is a changing in this, there is a change in the position of rod CD, right? So this is moving in the horizontal direction, right? So just to recap, if there is an angular velocity, if there is a rotating, due to the rotating rod AB, there is a motion in this rod CD in the horizontal direction. So if I write X, this X as L cos theta, this X should be changing in time because it's moving in the horizontal direction, this rod CD moving in the horizontal direction, which means that if I differentiate this with respect to time, I will get the X dot, the rate at which X is moving in time, as minus L sine theta, theta dot, right? And this is the velocity of CD. So in a similar manner, if I double differentiate this, I will get the acceleration CD, which is X double dot, which I can write as L sine theta, theta double dot, minus L cos theta, theta dot square. So it will be sine theta, theta double dot, plus cos theta, theta dot square. So this will be my acceleration of length CD, which is equal to X double dot. So my theta dot is omega, and my theta double dots, now my omega is constant, which means my theta double dot, which is supposed to be an angular acceleration, is 0 because my theta omega is constant. So now I can plug this quantity in the above expression to find the velocity and acceleration of length CD. So it will be VCD equals X dot equals minus L sine theta omega, so it will give me minus omega L sine theta, and the acceleration will be minus L sine theta. This is 0. There is no angular acceleration because the angular velocity is constant, so I will have cos theta omega square. So on simplifying, the acceleration of bar CD will be omega square L minus cos theta. So this will be my acceleration, and this will be my velocity of bar CD. So just to recap the problem here, we have given the mechanism such that we are given that this bar AB rotates in an angular direction, and due to this angular motion there is a horizontal translation of bar CD. It is moving in the X direction. If this is my X and this is my Y, so my CD is actually moving in the X direction, and we need to find the velocity and acceleration of CD, or the velocity and acceleration of X in the horizontal direction. So we wrote X as L cos theta. It is purely from the geometric perspective. and we know that x is changing with time, so we differentiate this expression in time, so we got the velocity of the bar CD, because whatever the velocity of x dot, it should be the same velocity as of CD, because both are moving in the same velocity. So my x dot will come out to be minus L sine theta theta dot, and if I double differentiate this expression in time, I will get the acceleration x double dot, which is given in terms of theta double dot and theta dot square. Then we have given that we know that theta dot should be the angular velocity, and the angular velocity is constant, so that my angular acceleration should be 0, and then we substitute this in the above expression of velocity and acceleration, we easily got the expression of velocity and acceleration. So it's pretty much straightforward problem. So we will solve a similar problem in the next one as well. So here, determine the velocity and acceleration of the follower rod CD as a function of theta when the contact between the cam and follower is along the straight region AB. On the face of the cam rotates with constant counterclockwise angular velocity omega. So it's a very similar problem. So here in this problem as well, we have given that the cam, which is this portion, it's rotating with the constant angular velocity, and due to its rotation, what happens, there is a horizontal translation in the bar CD, right? You can imagine, like, if this portion, let's say this is my cam and this is my CD, bar CD. So let's say at time equals t1, this is my position, and at time equals t2, this is my position. So you can see that there is this bar CD actually translate in the right direction, because this part come upside, and since this part is coming upside, this bar is moving in the right side. So there is a translation of CD in towards the right side, and it will have some velocity from which it is translating in the right side, right? It has some velocity, let's call it VCD, and at this velocity this bar CD tries to translating in the right direction, and this motion is due to this angular motion omega from the cam, right? So if this is my origin, this is my radius r, and this is my, let's say, xc, and this is theta, then I can write xc as r divided by cos theta, right? Because r is my x cos theta, so x will be r divided by cos theta, right? So it's basically r sec theta, and we know that this bar CD is actually moving with the velocity VCD, which is xc dot, right? And the acceleration of this bar ACD will be x double dot c. So basically what we need to do, so this is my xc, we need to differentiate this equation in time, and again we need to differentiate this equation. So when we do it first time, we will get the velocity x dot, and when we again differentiate this expression, we will get x double dot, or the acceleration of bar CD. So we have x equal r sec theta. If I differentiate this expression x dot c VCD, I will get r sec theta tan theta theta dot. So this is the velocity of the bar CD, right? Because x is the horizontal direction. So if I make a Cartesian coordinate, this is my xc and this is my yc, and x is the direction in the horizontal, it's a horizontal direction, and x dot will be the rate of change of this horizontal direction, which is actually the velocity of this CD. If I differentiate this expression again, I will get x double dot CD, which is the acceleration of bar CD, and it will come out to be R sec theta tan theta theta double dot plus, then we need to differentiate, so we differentiate this one, now we need to differentiate this, so we will have here sec theta, the differentiation of tan theta will be sec square theta theta dot. Now we have to differentiate this, so it will be, so the differentiation of sec theta will be tan theta sec theta, and here we have tan theta theta dot. So if I simplify above expression, I will have sec theta tan theta theta double dot. I can take common and I can club these two terms because these two terms have theta dot, and they should be theta dot square actually. So it will be theta dot square sec cube theta plus sec theta tan square theta, right? So in the question now we have given that it is rotating with constant angular velocity omega. So my theta dot will be omega and it is a constant, which means my theta double dot will be 0 because my d omega by dt is 0, it's a constant, which will give me theta double dot because this is equal to theta double dot. Now if I substitute this into the velocity expression as well as in the acceleration expression, I will have velocity of VCD, which is equal to r omega sec theta tan theta, and the acceleration will be r. So this term will be 0 because there is a theta double dot here. So I have theta dot square sec cube theta plus sec theta tan square theta. So my ACD will be r omega square sec cube theta plus sec theta plus tan square theta. So this will be my acceleration of the bar and this is my velocity of the bar. So you can see that the problem is very similar to the previous one, and it is just differed by the mathematical algebra, that you need to now differentiate the sec and tan theta terms, which appears to be a bit complicated, but you see there is a similar concept here. So you can see that in this question what happens, that there is a two-member body which we have given, and if there is a motion in one body, it will actually produce a motion in other body. And in this two problem we saw that if there is a motion, angular motion in one body, it will produce the translating motion in other body, that we actually are finding. So there is a very similar problem here. It's the same problem. So in this problem also we have given the block which moves to the left with a constant velocity v naught. Determine the angular velocity and angular acceleration of the bar as a function of theta. So it's the same problem. So in this problem we have given that this block is actually moving to the left direction, and as it is moving in the left direction, there is a angular velocity which is imparted to this rod. So in the previous problem we have an angular velocity which is there in one of the member, which results in the translating velocity of the rod. But here we have given the translating velocity of one member, which is this block, which is imparting some angular velocity and angular acceleration in this rod, and we need to find these quantities. So now you can see that since this block is moving in the horizontal x direction, so if this is my x, this is my y, and this block is moving in the minus x direction. This is my minus x direction, so it is moving in the left side. So my x will be a tan theta. So basically this is my a and this is my x. So I can use this trigonometric relation. So my x will be a cot theta. Now since the block is moving in the negative x direction, the x is changing in time, right? So there is a velocity v equals to minus x dot, because block is moving in the minus x direction. So v equals to minus x dot here. So if I differentiate this expression, I will have minus v equals x dot equals minus a cosec square theta theta dot. So this will give me the velocity of this block, and we know that omega is theta dot. So if I substitute the omega, which is theta dot here, I will have v equals a omega cosec square theta. So my omega will be v by a cosec square theta, and I can simplify this expression. So I can write this v by a sine square theta, because cosec theta will be 1 by sine theta, so cosec square theta will be 1 by sine square theta. So if I apply this here, I can write this 1 by cosec square theta equals sine square theta. So my angular velocity will be v by a sine square theta. Right, so this is my angular velocity. Now we know that my angular acceleration is rate of change of angular velocity, so we need to differentiate this expression here. So alpha d by dt, and here we have v by a sine square theta. So alpha, so v by a is a constant in time, I mean it's not a constant in time. So if I differentiate this expression alone, I will have alpha v naught by a. So this sine square theta will become 2 sine theta cos theta d theta by dt. So from the trigonometric relation, we know that sine 2 theta equals 2 sine theta cos theta. So this is one of the expression from the trigonometry, and we can use this here. So alpha will be v naught by a sine 2 theta d theta by dt, right? And this omega, we know that in the previous question we wrote omega as theta double dot or d theta by dt. So basically this omega is d theta by dt, right? So this d theta by dt is actually this v by a sine square theta. So we can substitute here. So we will get alpha equals v naught by a sine 2 theta v naught by a sine square theta. So alpha will be v naught by a whole square sine 2 theta sine square theta. So this is the angular acceleration of the rod, and this is the angular velocity we found. So you can see that the problem is very much similar that we have solved previously, but it is just more about the mathematical algebra here. So just to recap here, we have given this bar which is moving in the left direction. So we write down the distance it is covering, which is L, A or theta. Now when we differentiate this expression, we will get the velocity of block x dot and the acceleration of block. Now since it is moving in the left direction, we found that the velocity is minus x dot, not the positive x dot. So from this velocity expression, we can able to calculate the omega dot. So in the previous question, this was our final answer v, but here we need to find this omega dot, which is theta dot, which is omega. So once we calculate the omega, which is theta dot, we can actually easily calculate the angular acceleration, which is rate of change of omega by time, or d theta dot by dt. Both will give the angular acceleration. So we differentiate this quantity with respect to time to calculate the angular acceleration. And by using some mathematical manipulation, like using the trigonometric identities and all, we can able to arrive at the final answer. So this is our angular acceleration and this is our angular velocity. So until now we have solved the problem where we have given the multiple members connected to each other, and if one member is producing some motion, there will be a motion in other members. So first we look problems where one member is producing the angular motion and which results into a translating motion of other member. In this problem we saw that the member is actually producing the translation motion which is responsible for the angular motion of the other member. So you can actually easily calculate the velocity and acceleration of other member, whether it is a translating velocity acceleration or angular velocity or acceleration. Now we will solve the problems where we need to use the concept of relative velocity. So basically we will using the expression of relative velocity. So let's say you have a position vector at B, which is given as position vector of RA and position vector of B with respect to A. Now if I differentiate this expression in time, I can actually find the velocity of point B equals to velocity of point A and the relative velocity of point B from point A, right? So let me make a diagram. So this is my position vector at B and this is my position vector at A, and this is the position vector of B with respect to A, and there is a point here, initial point, and this is the final point, and there is a motion of this point from A to B. And Vb is the velocity of point B, Va is the velocity of point A, and this is the relative velocity of point B when you are standing at point A. So now in the upcoming problems, we will be using this expression to calculate the velocities and other quantities like accelerations. So we will be starting with a very standard problem. So here we have given h and theta. So h and theta, which is a known quantity, and we have given the speed of A and B, which is v. We need to determine the angular velocity omega of the body and direction of phi of Vb. So we need to calculate the angular velocity here, and we have given the velocity of point A and point B, which is v. So we can write down the expression of relative velocity. So basically we will be writing the velocity of point B, velocity of point A, and relative velocity of point B with respect to A. So it will be And this relative velocity of B with respect to A can be written as omega cross position vector B with respect to A. So we have omega cross R B with respect to A. So this is the expression. Now we have given that the velocity of B and velocity of A is V. And you can see this is a two-dimensional problem. So basically the problem you can define in x and y coordinate. So this is a two-dimensional problem, which means the velocity vector A and B should be defined in x and y components. So in the equation we have given that the velocity vector VB and velocity vector VA is V, which means VB will be, so here VB, the horizontal component of VB is moving in the minus x direction, right? So it will be minus V cos phi in the horizontal direction plus V sin phi, because it is moving in the positive y direction here. V sin phi in the y direction, and the velocity of point A. So if I consider point A here, it is moving in the positive x direction and positive y direction. So it is V cos theta in the x direction plus V sin theta in the j direction. And we have given the angular velocity here, omega, and the direction of angular velocity is k, which is coming out from the screen, right? So this is my x and this is my y, and this is my direction z. So this is basically z direction is coming out from the screen. Omega k, this is minus omega because it is moving in the clockwise direction. So clockwise direction I am assuming is minus cross product with RBA. Which is minus HJ. So my H in the y direction. It's a vertical direction. It is in the y direction. So this is the y component, right? So this is my equation. So I have write down the equation in the vector form, which has both x component as well as the y component. Okay, so from the basic vector algebra, you know that if you do the cross product, right? So here we did the cross product of a component in the k direction and in the j direction, and you know that if you do the cross product of k and j, the resulting quantity will be in the I direction, right? For example, if you do the cross product in I and j component, you will get the resulting quantity in k. If you do in j and k, the cross product between j and k, you will get the resulting quantity in I. If you do the cross product in I and k, you will get the resulting quantity in the j component. So here we will get the resultant quantity of this vector product here in the I direction. So now, since we have given the vector quantities and it has both x and y component, we need to separate the x and y component, right? So my x component is given in blue color. So this is my x component, this is my x component, and this entire magnitude of the vector product is in the x component. So my x component will be minus v cos phi equal to v cos theta plus minus omega h, right? So this is one of the equation in the x component. Similarly, in the y component, I can write in the red color. So this is my y component, it's in the j cap direction. This is also my y component. So it is v sin phi equals v sine theta. So this is my another equation. So you can see that sine phi equals sine theta, which will give you phi equals theta. So your phi is in actually theta direction. So as your theta is increasing or changing, phi is also changing in a similar manner. So both are equal angles. So this we got from this y component of equation. Now from the x component equation, we can substitute this result in the x component equation. So we can write down minus v cos theta equals v cos theta minus omega h. So minus v cos phi this is theta minus v cos theta. So this will become theta equals minus omega h. So it is 2v cos theta equals minus omega h. So my omega will be 2v cos theta by h. Right, so this we got the angular velocity of the body, which is 2v cos theta by h, in the relation of angle phi, which is equals to theta. So just to recap, we have given the 2 points here, and we have given the velocity of 2 points, and we need to figure out the angular velocity. So since we have given the 2 points, we actually use the relative velocity component, because it will connect the velocity of 2 points. So it will so here you can write the velocity of point B with respect to velocity of A. So basically this will give you the relation of one point velocity to the another point velocity, and we have given the velocity of 2 points, which means that from the relative velocity expression of the relative velocity component, you can actually figure out the velocity of one point if you have given the velocity of other point, right? So since it is a two-dimensional problem, I write the velocity in the component manner, and then we separate out the x component and y component. So we got the two equations, and from this two equation we can able to find the result of angle phi and the angular velocity v. So if you have any doubt, you can ask. So let's solve few more problem like this. So we will be using now same concept, same expression of relative velocity in all the problems, and we will see that how to solve a bit different problems each time from the same expression. So here we have given the block. If the block at C is moving downward at 4 feet per second, determine the angular velocity of bar AB at the instant shown. So this block C is actually moving in the downward direction, and as it is moving in the downward direction, we need to find the angular velocity of it. Right, so this is my bar B C, and this point is moving downward. Right, so at this point is moving downward, it will have some angular velocity, which is omega BC, right? And this is point A, which has the rotation, which is given in the equation, that it has a angular velocity which is AB, right? So from the basic kinematics equation that we have discussed from the last week, we know that if this rod, which is having angular velocity omega and a distance r, then the velocity, translating velocity v, can be found out by r omega, right? So here also we have given this angular velocity omega av, and we have given the distance, we have given the distance, which is 2 feet here. So by using this relation, we can actually find the velocity at of this point, right? So basically the velocity of point P can be written as R omega AB. So it will be B. R is 2, so it will be 2 omega AB. So it's very similar to the previous problems. Like before the relative velocity problems, we have discussed that if we have given the motion of one member and the other member is connected to it, then how to find the velocity of other member. So it's a very similar concept. Like here we have given the motion of this member, but we can able to find the velocity of this point, which is actually located at point B, right? So now we have given the velocity two velocity here. So we have given the velocity of v at point B, we have given the velocity at point C. So we can use the relative velocity expression between point B and C to see how the velocity at point B changes with respect to C. Because as I told, if you have given the velocity at 2 points, then you can use the relative velocity expression between these 2 points. That what we have done in the previous problem, that we have given the relative velocity at A and B, and we actually connect the velocity between these 2 points by this expression Vb equals Va plus omega cross Rbn. So here also we can write the relative velocity expression as Vc equals Vb plus relative velocity of Vc with respect to B. So this can be written as Vc equals Vb plus omega Bc cross R Bc, right? And we have already given this Vc and Vb. We found Vb as 2 omega AB, and we have already given Vc in the equation, which is 4 feet per second. And just notice that this Vc is going downward. So, and this is again a two-dimensional problem, which you can define in x and y axis. And this Vc is going downward, which means that this 4 feet per second, which is Vc, is in the y direction, negative y direction. So in the end, we need to write down the velocities, these quantities in the vector notations, right? So my Vc is minus, because it's going in the negative y direction, minus 4 j cap. There is no component of horizontal velocity here at point C. Similarly, Vb, since it is going downward here, we have 2 omega AB, and it is going in the negative y direction, so this is also minus, and it is in the y direction, so j cap plus. Now omega, you can again see that there is a omega which is in kth direction, that is in the z direction. And the z direction is out of the screen, out of your screen is the z direction, so it will be omega bc k in the kth direction, cross product with, you have to take the cross product with this vector, this is our rbc vector. So in the previous question, the rbc was alone in the y direction, which is h in the z direction, in the y direction, sorry. So you write h as a j component because it's entirely in the y direction, but here it is, it is in the both direction, x and y. So basically, if this, you can take, you can actually write down the x and y component. So this is the displacement vector, and you have given the 30 degree angle. So this quantity will be, and the length is 3 feet. Length is 3 feet here. So it is 3 cos theta in the x direction plus 3 sin theta in the jth direction, right? So now you actually write down the expression for the velocity, relative velocity of point C with respect to point B. So this is our expression which is given in both x and y component. So now you need to separate the x and y component. So again I am writing the x component in the blue color and y component in the red color. So as we discussed in the previous problem, the cross product given in, you are actually taking the cross product of k vector and with I and j vector. So if you take the cross product of k with I cap, you will get jth component. If you take the cross product of k with respect to j cap, you will get ith component, right? So this and this cross product will give you the ith component, because this is k cap into j cap, which will give you ith component, and this one will give you jth component, because k, when you do the cross product of k cap with I cap, it will give you a j cap. So this will give you the j component, and this will give you the ith component. So you will have, and this is j component, this is in the y direction. So in the x direction, you will have equation 0 equals omega bc multiply 3 sine theta, right? And here you got that omega bc is 0. So when you write down the jth expression component in the y direction, you will have minus 4 equals minus 2 omega. This is omega AB. This is the angular velocity of rod AB. The angular velocity of rod BC is 0, which means this is 0. So there is no point of writing this part of the expression. Because omega BC is 0. So omega AB is 2 rad per second. So this is the required quantity that we need to find. The angular velocity of AB come out to be 2 rad per second. So just to recap here, so here we have given the velocity of point C, which is moving in the y direction, and we need to find the angular velocity of rod AB. So in this question we actually use two concepts. The first concept is from the absolute motion that we have seen in the first three problems in the beginning of the class, that if you have given the one component member and it is connected to the other members, and if you have given the velocity and acceleration of one component, then how to find the velocity or acceleration of the other component. So we use this concept to find the velocity at joint B, because we have given the angular velocity here and we have given the distance. So from this expression you actually find the translating velocity of joint B. So once you got the velocity of joint B, you have already have velocity of joint C. You can use the relative velocity expression between these joints that we have done here. And from this expression, you write down the vector expression and you separate them on the basis of x component and y component, and you will get two equations. So in the first equation we found that omega bc, that means the angular velocity of this bar is 0, that we got from the x component of velocity, and from the y component of velocity we got that the angular velocity of AB, this bar, is 2 rad per second, which is the required angular velocity we need to find. So any doubt? So again solve the similar problem here. So here we have given the flywheel. So this is the flywheel. If the flywheel is rotating with the angular velocity of omega a, which is 6 rad per second, determine the angular velocity of rod BC at the instant shown. So we have given the angular velocity of flywheel, which is omega a 6 rad per second, and we need to find the angular velocity of this rod BC. So again we will be using two concepts. The first concept is due to the movement of this component, which is flywheel, what is the velocity of point B, translating velocity B here. And in a similar manner, due to this angular velocity of this CD, what is the translating velocity VC, right? Now since this angular velocity, there is an angular velocity of this flywheel VA, this is a flywheel which has a radius 0.3 meter, then it should have some translating velocity at this point, right? Which will be given as V equals R omega. So this is VB R omega A. So VB R is 0.3, right, multiply by 6. This omega is 6, so VB is 1.8 meter per second, right? So we got the magnitude 1.8 meter per second. In order to get the sign, whether it is plus or minus, you need to consider this as a vector quantity. So here I have written the expression R omega in terms of magnitude. If you write this expression VB in terms of a vector, it will come out to be omega A cross R, right? So this omega is 6, it's minus 6 k cap cross 0.3 j cap. So you can see you will get the same magnitude 1.8 meter per second, but now it's a negative direction, which means the velocity VB is toward downside, assuming that this is my coordinate system. So VB is in the downward direction. So for the sign, always use the vector notation, because if you use the magnitude notation R omega, you will get the magnitude, but you cannot decide the sign whether the velocity is in the up direction or in the negative direction. But if you use the expression in the vector notation, you will actually get the sign here. So for the omega, I always use clockwise as a negative direction. So this is minus 1.8 meter per second, which means the velocity of point B is in the downward direction. Similarly, I can find the velocity at point C, which is omega CD cross product with RC. So here previously this was the jth component, right? But here this has the x and y both component. So RC has both x component as well as y component. So omega CD is again in the kth direction, because if a rod, so this is my rod CD, if this rotating with omega CD, the component of omega will be coming out to your screen, which is kth component. Okay, so it is moving in the counterclockwise, which means it is omega CD kth cross product with RC. So your RC will be, so this distance is 0.6 meter and it has an angle of 60 degree. So it is 0.6 cos 60 in the x direction plus 0.6 sin 60 in the jth direction. So in the previous lecture, actually I have discussed about this. So how to differentiate between displacement, which is a vector quantity, and distance, which is a scalar quantity. So basically we have given the motion in a random direction, the body is moving in the random direction, then how to find the displacement, which is a vector quantity, and how to find the distance of the same body, which is a scalar quantity, and in the next problem we actually use the same concept to find the displacement vector. Sorry. So using the similar thing, we are actually writing this displacement vector here. So this is my displacement vector RC. So now I can write velocity of point C. So as I said, if you take the cross product of k cap with I cap, you will get the resultant in the jth cap. If you take the cross product of k cap with j cap, you will get the resultant quantity in the I cap, or in the x direction. So if I take the cross product of this quantity with this one, I will get the quantity in the jth cap, or in the y direction. So this will be omega CD point 0.6 sine 60 j cap, and if I take the cross product of this quantity and this quantity, I will get the resultant quantity in the x direction, or I can write this as that is in the I cap. So it will be omega CD 0.6 sine 60 ith cap. So this should be cos 60. Right, so this is my ith component and this is my jth component. So I will get the velocity here. Right, so I got the velocity here at point C, and I got the velocity at point B, and this is actually ith component because I take the cross product of k and j, so it will give me the velocity in the ith direction. So once you got the velocity at point B and point C, now you can use the relative velocity expression between these points. It has some angular velocity omega bc, so I can write velocity at point B equals velocity at point C plus the relative velocity. So BB is minus 1.8 in the ith direction that we found here, and VC is this quantity, which is 0.6 omega CD sine 60 ith cap plus 0.6 omega CD cos 60 jth cap. So this is my velocity at point C plus omega BC. So this omega BC is in kth direction, cross product with this, which is the length of this bar, which is 1.5 meter in the horizontal direction. so which is 1 minus 1.5 in the horizontal direction. So this is our vector equation of the relative velocity. Now we need to separate out the x and y component. So x component, the x component we can write as minus 1.8 equals 0.6 omega CD sine 60. That's it. So this is from x component, and from y component I can write as, so there is no y component at the left hand side, so it's 0 equals to this one, 0.6 omega CD cos 60 plus this one minus 1.5 omega BC. So this is my equation 2. So if you write down this vector notation, vector expression in the x and y component, you will get two equations. So from the first equation we can actually calculate the omega CD, and once you get the omega CD, from the second equation we can calculate the omega BC, right? So your omega CD will be minus 1.8 divided by 0.6 sine 60. So it will give you the omega CD, which is minus 3.468 rad per second. Now you substitute this expression omega CD in the equation 2, which is actually the y component of this vector equation. So 0 equals 0.6 multiply minus 3.468 cos 60, which is 1 by 2 minus 1.5 omega BC. So now we can here find omega BC, which is 1.5 omega BC equals 0.3 multiply 3.468. So you will get 0.693 rad per second. Just a minute. Paula. So this is your omega BC. So it's a very similar problem actually. Just to recap how we did it. So we have given the angular motion of this flywheel, and we have been asked to calculate the angular velocity of this rod BC. Okay, so what we did, from this angular velocity we actually tried to calculate the translating velocity of this point BB. From this angular velocity we actually try to calculate the translating velocity of point C, and this we have done from past 5 questions since morning, because we are doing these things from the first question itself, right? So basically you are given one component, one member, and you have given the velocity of one member, then how to calculate the velocity of other member. Now once you figure out the velocity of these 2 points, you can use the relative velocity expression between these 2 points, and we write down the relative velocity expression between these 2 points, which is given in this green box, And now since this is given in the vector quantity, you need to separate the x and y component expression. So you will get two equations, equation 1 and equation 2. So from the first equation you will get omega CD, because you need omega CD to find the final answer, omega BC. So first you get the omega CD here, then once you calculate the omega CD, you can actually calculate omega at bar BC. So in this question there is nothing new. The only little thing is there, you need to first find the velocity at these 2 points in order to calculate the omega. Right, because if you are going to use a relative velocity component, you should know velocity of these 2 points that you can find from the given angular velocity of this flywheel and this component CD. So any doubt that can ask. So let's move to the next problem. So it's pretty simple problem we have. So here we have given the pinion gear A rolls on a fixed gear rack B with an angular velocity of 4 rad per second. Determine the velocity of the gear rack C. So basically, let's say this is my gear B and this is my gear C. And we have given the velocity of this angular velocity of this component A. So we need to find the velocity of VC, and we have given that this is fixed. So the bottom gear is fixed, which means the velocity of VB equals 0. Right? So now we can actually use the relative velocity expression between point C and point B. And we have already given that velocity at point B is 0, so my velocity at C will be omega cross RCB rectangle. Now omega we have given 4 rad per second, which should be in the k direction. Omega is 4 in the k direction. You can see it's a counterclockwise, which means it's positive, and this is my R. RCB, which is 0.3. So the radius is 0.3. So this is 0.3 and the remaining is 0.3. So total is 0.6 in the jth direction. So 0.6 in the jth direction. Now if I take the cross product of this, I will get the magnitude in the ith direction. So my VC is 2.4 in the ith direction, feet per second. So this is my velocity at point C, 2.4 in the x direction, feet per second. So this velocity at point C is in the positive x direction. It's moving like this, the direction of velocity in the positive x direction. So it was a pretty straightforward calculation, because we have given the velocity at point B is 0. Otherwise we need to find the velocity at point B from this motion, and then we could have used this expression, which what we did in the previous question. So let's consider another question, similar problem, but here the velocity of B is not 0. So now the pinion gear rolls on a gear tracks, and if B is moving to the right at 8 feet per second and C is moving to left 4 feet per second, determines angular velocity. So now it's a similar setup, but what happened that now this point P is moving in the right side and this point C is moving in the left side, and there is an angular velocity here. We need to find this angular velocity. So now the difference is the velocity at point B is not 0 and the velocity at point C is in the left direction. It is in the minus x direction. So again we have to write the relative velocity expression between point C and point B. So from this expression, because we have given these two, Vc and Vb, we also know this quantity. We can actually easily find the omega, right? So my Vc is in the negative x direction because it's in the left side. And the Vc, magnitude of Vc is 4 feet per second, so it is minus 4 I in the x direction. Vb in the right side, positive x direction, it is in the positive x direction, and the magnitude is 8 feet per second, so it is 8 I. Omega we need to find, which is in the kth direction, cross product with displacement vector of RCB, this displacement vector, which is 0.6. So until now it's the same problem. Only difference is instead of this velocity is 0, now it is given 8 in the x direction, in the positive x direction. So now you have got the vector equation here. So you can separate out the x component and y component. And here you can see that there is no y component because the quantity, this is the cross product of kth component with jth component, and it will give you the quantity in the x direction. So this whole quantity is in the x direction. It will write, you have to write it down in the ith cap. So all the terms in the x direction. So there are no terms in the y direction. So it will be simply 4 minus 4 plus equals to 8 plus 0.6 omega. I'm just writing out down the magnitude here. So it is minus 12, minus 12 equals 0.6 omega. So omega is 12 by 0.6, which is minus 20 rad per second. Minus 20 means the direction of omega is in the clockwise direction. So I can write this omega vector as minus 20 k cap rad per second. So this is the angular velocity that we need to find. Now we also need to find the velocity at centering. So until now we found the angular velocity of point A. So now we need to find the translation velocity VA. So what we can do, we can take point A, which is this, and point B, which is this, and write down the relative velocity expression like this between point A and point B. Earlier we did between point C and point B. Now we are doing the same with point A and point B. So here VA, which is unknown quantity, equals VB plus omega cross RAB. This is unknown quantity, we know this, and we also know this. So this RAB, which is this displacement vector, is 0.3 in the y direction. So velocity vector at point A will be equal to, my VB is 8I, which means 8, VB is 8 in the positive x direction. Omega is minus 20 in the kth direction, cross 0.3 in the y direction. So here you can see that this quantity will be in the x direction, in the ith direction. So it will be 8i minus 6i. So VA will be 2i feet per second. So VA will be 2 feet per second in the positive x axis. So this VA is moving here in the positive x direction. This VB is moving in the positive x direction, but this point is moving in the negative x direction. This is what we have given in the question. And we found A is moving in the positive x direction with 2 feet per second magnitude. So just to recap here, this is kind of part B of the last question, where we have given the velocity of VB equals 0 and we will be asked to find the velocity at point C. So we use the relative velocity concept between these 2 points. Here in this question we have been asked to find the omega, which is the angular velocity of point A, and the translation velocity VA of point A here. So first we use a relative velocity concept between point C and point B. We solve this equation to find the omega. Then we use the relative velocity expression at point A and point B to calculate the translation velocity VA. So let's move to the next problem here. So if the gear rotates with an angular velocity omega 10 rad per second and the gear rack moves at Vc 5 meter per second, determine the velocity of the slide block A at the instant shown. So let's write down the relative velocity expression between point B and C. So it will be omega cross RBC vector. This is point B. So since Vc is moving in the horizontal direction, in the negative x direction, this is my coordinate system x and y, and you can see Vc is moving in minus 5 x direction. So this is my velocity vector at point C. So my velocity vector equal to minus 5 I omega in the kth direction, which is 10 k. It is in negative direction, but it's a clockwise rotation, cross product with this distance, which is 0.075 in the y direction. So every component in the ith x direction, so this is an x direction and this whole quantity in the x direction, because it's a cross product between k cap and j cap. So it will be minus 5i minus 0.75i. So VB will be 5.75 minus I meter per second. Now I can use the relative velocity between A and point B using the same expression. So we already know B, so we need to find A. So if you substitute VB here, and this R will be this vector, so it has both x and y component, which is minus 0.5 cos 60 in the ith direction plus 0.5 sin 60 in the jth direction. So this vector you need to write down in the x and y component. So if you write down in the x component, you will get this is when you write down the y component. So from this two equation you can actually find VAB, which is 2.45 meter per second. So it's a similar problem here. Again we split into x and y component to get the two equations. One equation will give you this unknown quantity omega AB, and one equation will give you this translation velocity at point A. So that's it for today. So today we have solved a couple variety of problems. So we start with problems where we found the velocity and acceleration expression in the polar coordinate. Then we move to the absolute motion where we have given the multiple component connected to each other, and we have given the velocity. It can be either angular velocity or translation velocity. If we have given the angular or translation velocity of one component, we can actually find the same thing for the other component, and we have solved a couple of problems related to that. And then we move to the relative velocity problem where we have given the velocity of 2 points, and we can write down the expression of relative velocity between those 2 points. And we found the unknown quantity there. We also solve problem where we use both concepts, like the first concept where we have given the two members and we have given the velocity of one member and we need to find the velocity of other member. Then we use the relative velocity component. So we use both two components in a single question, and we solve such multiple question like that. And so we thoroughly discussed the concept of the governing equation that you have to use in these questions. The only differ is that in the mathematical algebra, that in the two-dimensional case you need to define the vector quantity first. So in some case you saw that the displacement vector quantity only have one component, and in some question the displacement vector has two components. So it's mostly the change in the mathematical treatment, but otherwise the concept was the same in all the questions. So that's it for today.